Speaker is Stephen Chuang from the University of Akron, who's going to speak to us about transient infrared study of adsorbates in heterogeneous catalysis.
Good afternoon. The subject I'd like to discuss with you this afternoon is transient infrared study of adsorbate in heterogeneous catalysis. First of all, I'd like to acknowledge the graduate students, Mike Balagos, Mark Brandich, and Roger Christmas has performing these experimental works. Determination of the reactivity of adsorbates is essential for developing an understanding of heterogeneous catalysis. The reactivity of adsorbates depends on the chemical environment of the catalyst surface. This reactivity usually depends on the partial pressure of the reactants, temperature, and surface compositions. And adsorbate can also induce a surface restructuring, which in turn can modify the reactivity of adsorbate. Therefore, the reactivity of adsorbate should be studied under the reaction conditions. As pointed out by Bob Eichen more than 35 years ago, the infrared spectroscopy allowed the institute study of adsorbate under the reaction conditions. And FTIR permits the rapid scanning of adsorbate, so we can combine the FTIR technique with the various kind of transient approach to study the dynamics and the reactivity of adsorbate. So combining this infrared spectroscopy with a transient technique will allow us to obtain the mechanistic information and to distinguish the reaction intermediates from the spectator species. The transient techniques can be used to obtain the information about the surface coverage and residence time of the reaction intermediate. And infrared spectroscopy can be used to obtain the information about the surface coverage of IR observable species. And with the infrared, and we can observe the adsorbed species under the reaction conditions. And we can treat we don't have to treat the catalyst surface as a black box. The objective of our study has been to determine the reactivity of this adsorbed CO for CO insertions, and also what type of adsorbed CO involved in the NO-CO reaction on the supported loading catalyst. The structure and the vibrational frequency of this adsorbed CO on the surface of loading catalyst has been well established. For example, the CO can adsorb on a reduced loading surface as a linear or bridge CO. And CO can also adsorb on the oxidized loading surface as a gem-dicarbonate or linear CO with these high weight numbers. And it has also been suggested CO can adsorb on this manganese or the cesium for multi-loading catalyst, and in the form of this tier forms. All these different adsorbed CO exhibit the different vibration frequency. So the infrared spectroscopy is an excellent technique to study this reactivity of these various types of CO. And here is the experimental apparatus we use for this transient infrared study of these CO insertions and the reaction of NO with CO. And this experimental apparatus includes 3 sections. The first part here allows us to inject the reactant to the infrared reactor cells in various forms, in the pulse form or step forms. And the reactant earthens, the earthens from the composition of earthens from the IR cells will be analyzed by mass spectrometers and or gas chromatographer. The infrared cell we use for this study can be operated up to 500 degrees C and 60 atmosphere. The catalyst is placed in the form of the thin disc and placed in the center of the cells. And we use a bichrome O-ring to seal the calcium fluoride window here. And bichrome O-ring can only stand up to around 260 degrees C, so we have to use cooling water to pour this part of the infrared cell. The dead bottom of this infrared cell is filled up with a 2 calcium fluoride window rod here, so that this catalyst disc is holding by this calcium fluoride window rods here. And the thermocouple is inserted and touch the catalyst disc, and reactants coming in and going out. So we can use this cell to operate the reaction in a batch mode or semi-batch or steady-state conditions. Okay, this infrared cell has been used to study the CO insertion in ethylene hydro formulation and also NO-CO reactions. Okay, the first set of the result I'd like to discuss with you is the infrared study of the CO insertion during this ethylene hydro formulation. Let me briefly explain to you about ethylene hydro formulation here. We have been using this ethylene hydro formulation as probe reaction to study the sites for CO insertion, which is one of the key steps leading to the formation of high oxygenate in the Fischer-Tropsch synthesis. In the ethylene hydro formulation, okay, in this reaction, the reaction involved with three reactants, which is ethylene, hydrogen, and CO. And there are two major products are produced from this reaction. One is ethane, and one is propanoaldehyde. In this reaction, ethylene is first partially hydrogenated to form the ethyl species, and this ethyl species can undergo the hydrogenation to form the ethane, or it can also undergo this what I so-called the CO insertion here, because CO is inserted between this carbon and metal here. And this insertion usually is in the form of a migratory insertion. And this insertion will form the alphyl species, and this alphyl species will be hydrogenated to form a propanoaldehyde. So we have studied this reaction on the loading catalyst. This is a silica-supported loading catalyst with a 3% of loading. The catalyst particle size, the loading particle size is around 90 angstroms. The first thing we did here is to reduce the catalyst, and this catalyst was prepared by rolling nitrate. It was reduced at 400 degrees C in fluorine hydrogens. And then we expose this catalyst to the CO at room temperatures. We can see the CO can resolve on the sodium surface as a linear CO, rich CO, and gem dicarbonyls here. Then after that, we expose this adsorbed CO to the ethylene and hydrogen at 1 atmosphere condition. The ratio of ethylene and hydrogen is 1. As you can see here, this adsorbed CO starts to react with these ethylene and hydrogens, lead to cause the formation of this propanoaldehyde here. This is the alphyl CO vibration frequency of this propanoaldehyde here. As propanoaldehyde formed, the linear CO was consumed. And there is very little change in the intensity of the bridge CO and gem dicarbonyls. So with this result, we can easily conclude this type of adsorbed CO is a linear CO. And the linear CO is the type of CO involved in the CO insertion leading to the propanoaldehyde. At the same time, you can also see that ethylene was hydrogenated to form ethane. In order to conform this result, we have also studied the sulfur poison loading catalyst. We use the sulfur to poison the bridge CO, and we still found the catalyst with a linear CO, which is active for the CO insertions. And we also used the silver to block the bridge CO side, and we found out the catalyst with the silver as promoters remain very active for the hydro formulations. In these reactions, the ethane and propanoaldehyde are the major products, and the selectivity of this reaction strongly depend on the reaction conditions, especially the reaction pressure. As you know, in the Fischer-Tropsch synthesis, usually you need to conduct at high pressure to produce oxygenate. So we are wondering what is the pressure effect and how pressure affect this CO insertion leading to formation of the high oxygenate. So we try to study this reaction at different pressure. So at this time here we pass the reactants, the 1:1 ratio over the catalyst under steady-state flow conditions. And we measure the rate at different pressures. And here are the Arrhenius plots. From this plot, we can see as pressure increase from 1 atmosphere to 4 atmospheres. The increase in the pressure causes a decrease in activation energy for the formation of propanoaldehyde. However, the pressure has very little effect on the hydrogenation of ethane to ethylene to form ethane. And it should be noted that this reaction was operated in the diffusion-free region. So we have checked, tried to make sure this reaction is operated in the diffusion-free region here. So this activation energy number is very low, and we believe this is intrinsic activation energy. We have checked it several times with this Weiss-Plato criterion and various kind of reaction engineering approach. Okay, let's take a look at the instituting for a spectra of this ethylene hydro formulation at different pressures. As we increase the pressure from 0.1 atmosphere, the 1 atmosphere to 5 atmosphere here, you can see the the increase in the pressure, increase in the pressure causes an increase in the intensity of the anemia CO. These are the gas phase adsorbed hydrocarbons and ethane species. And here is the anemia bridge, and these are the gas phase CO bands. As pressure increase, the reactor is filled out with the gas phase CO, so you can see there is an intense gas CO band here. So the increase in pressure from 1 atmosphere to 5 atmosphere causes around 10% increase in the coverage of the CO. And it appears to be very difficult to relate the change in activation energy for propionaldehyde formation with this increase in the CO coverage. So we have decided to use this transient technique to study the effect of pressure on the residence time and the coverage of the intermediates. The technique we use is a post-transient technique. Okay, this technique is equivalent to what is commonly used in the steady-state isotope transient technique, which is a step transient technique. Let me briefly explain to you how this technique works. Okay, the first thing we do is put the catalyst in the reactor cell, then expose this catalyst to the steady-state flow of ethylene, hydrogen, and carbon monoxide. So under the steady-state flow conditions, propionaldehyde is produced, ethane are produced. At a certain moment, we replace 10 cc of C12O by 10 cc of 13CO by a GC gas sampling valves. In this way, we can introduce a pulse function to the reactor systems. And this 13CO will be incorporated to the products, will be incorporated to the propionaldehyde. So from this 13C propionaldehyde response, we can obtain the residence time of intermediate leading to these specific products. And this response, we call it a pulse response. And from reaction engineering theory, we know the integration of pulse response with respect to time equal to step response. There's one advantage of using this approach here is we can use only 10 cc of the 13CO to obtain the transient informations as those obtained by step approach. So the step approach will require use of a significant amount of 13CO, and it will be very expensive to use a step technique to study the transients under the high pressure conditions. So now, the next is I'd like to show you is the result of the post-transient response during the ethylene hydroformylation here. Okay, this is normalized transient response. And here is the result of the analysis of the gas analysis of composition of the gas effort from infrared reactor cells. Okay, again, the catalyst was exposed to the steady-state flow of the CO, H2, and ethylene. And the regular CO we have here contains 2% of argon. We use 2% of argon here because the argon is not going to absorb on the surface of catalyst. So this argon response curve will tell us the flow pattern in this of the reactant flow in the reactors and the transportation lines. So as you can see this, when we switch 12CO to 13CO, 12CO concentration drop, 13CO concentration increase, and the 12CO lag behind the argon response curve is indicate the CO absorb and dissolve on the catalyst from the catalyst surface. And the symmetrical response of 12CO and 13CO suggests the 12CO was replaced by 13CO, and then 13CO was replaced by 12CO at 1-to-1 ratios. So basically, the catalyst surface was maintained at the steady-state conditions, except there is a change in the isotope compositions. And here, the propionaldehyde response here, this response far lag behind the 13CO is indicated it takes times for the propionaldehyde to be produced. And this is a pulse input, this is pulse response. So we use the process control approach to model this response curve so that we can obtain the rate constant for these proposed elementary steps. And the next set of results I'd like to show you is the infrared spectrum in these pulse transients. Okay, the first thing here you can see here is at the beginning we have anemia CO and bridge CO. This is a 12CO species. Then we switch to the 13CO, then 13CO is switched back to the anemia bridge CO again, to 12CO again. So this time here corresponds to the time we have seen here. It's about less than 1 minute. So this result here indicates there's a rapid exchange between the gases CO and the adsorbed CO here. And these are the different spectrum here. Just want to make sure there's a rapid exchange between the gases CO and the adsorbed CO. The next set of results is transient response at a higher pressure condition under the same temperature, at the same temperatures. Okay, again, I want to emphasize, I want to point it out here, this response going up and down is simply because the ethylene fluorometer we have was not able to operate at high pressure and we have trouble to control it. And one result here, we think that at high pressure, the propionate response is moving closer to certain CO. So it takes less time to form the propionate at higher pressures. So we have used a compoundable model approach and use those techniques in the process control to model this rate constant here. Basically, I would like to do here is to report this result, and the detailed modeling has been submitted for publication in Journal of Catalysis. From this modeling result here, we found the rate constant for hydrogenation of airfield species is increased with the reaction pressures. And coverage of adsorbed alkyl is also increased with the pressures. And the pressure has very little effect on the desorption of propionate types. So with this, I'd like to briefly summarize the effect of pressure on the reaction. Well, we found the pressure decrease the activation energy for propionate formations, increase the rate constant for hydrogenation of airfields species, and increase the coverage of adsorbed intermediates. And certainly, we also found the linear CO participate in the CO insertions. The last set of results I'd like to show you here is the infrared study of NO-CO reactions. Okay, in this case, this is a rhodium catalyst prepared from rhodium chloride. This is 40% rhodium catalyst, which was reduced at 400 degrees C. And this catalyst was undergo a couple of NO-CO reaction study. Then, initially we can observe linear and bridge CO, but after a 3-hour study, we only have linear CO left. And so we reduced the catalyst again at 400 degrees and bring the temperature down to around 200 degrees C, then expose the catalyst to a steady state flow of CO. When we expose this catalyst to a steady state flow of CO, we see the linear CO, gases CO here, and CO2. Then after that, we pause 10 cc of nitro oxide, 10 cc of nitro oxide in the steady state flow of the CO. So you can see the NO will come in, absorb as NO minus. And this is a gas NO species. As we pause the NO species into the reactor system, it causes the formation of increasing the formation of the CO2. This is a composition of the gas coming out from the infrared cell. In the first pause, you can see there's a big peak of the 44 here. These 44 peaks correspond to the CO2 and N2O. And we also performed the gas chromatography analysis. We found 10% of this peak is due to the N2O, which can be seen here. And during the NO pause, NO will absorb as NO minus, and the NO pause also caused the development of the gem dicarbonyl band here. And you can also see there's a big this isocyanide peak slowly developed. In the second NO pause, we see less amount of CO2 was produced, and we see after the second NO pause, we see the big gem dicarbonyl band was developed. After the third pause, we can even see the stronger band of gem dicarbonyl bands. So you see again this amount of CO2 was produced. So with this result, we can see here is the catalyst containing linear CO seems to be more active for CO2 formation than those catalysts containing gem dicarbonyls. So from this result, we suggest reduced sodium side, the can result linear CO are more active for CO2 formation than those rhodium cross sides that can resolve the gem dicarbonyl species. And this conclusion is consistent with what has been observed by the Professor Gonzalez a few years ago. We found that linear CO is more active for CO2 formation during CO oxidation over rhodium catalyst. And with this, I'd like to conclude my talk here. The Institute infrared technique coupled with the transient approach is an effective tool to study the reactivity of adsorbates. Thank you.
Thank you. Do we have any Questions? Yes.
You mentioned about NOCO reaction. Has this reaction practical importance?
Reaction of NOCO?
Yes.
It's for automobile catalysis.
Yeah, Keith.
Yeah. I was wondering, it would seem in this particular study you have no spectator species, am I correct?
Well, they are spectators.
Which, could you distinguish the,
In NOCO or
no, the insertion reaction?
insertion. Basically, we found this guy, rich CO and gem bicarbonate.
They go
Rich
on
CO
the
are
line,
they don't react.
but you can sort those out from the transient species. That's very interesting.
But it is usually depend on reaction condition, and this is at room temperature. So at room temperature, we can say this is at much lower reactivity. And in fact, we also found gem bicarbonate can react to form the aldehyde under different conditions, under much higher temperature conditions. So it really depends on the condition. But under this condition, this has lower reactivity. And we are not so sure whether it's react or not. It certainly has less reactivity than the linear CO.
I have one other question. Towards the end of your talk, you showed the isocyanate species
Yes.
apparently bound to the support. Okay.
That's
Have you got
what-
any idea how the CN bond forms?
It has been proposed in the literature, so it's usually formed on the metal surface and slowly migrate to the silica surface. And
True, but I mean, what reacts with what to form an NC bond?
usually, if you put, I cannot remember exactly, usually put CO first and put NO later, then you get the change.
You think it's CO reacting with atomic nitrogen on the rhodium surface?
Yes, yeah, that's what's
And
proposed.
then that migrates, you think, to the sport?
Yeah, I have to go back to check my data again because there are a couple spectrum here. We can check how it's migrated to the support because it's initially formed on the metal surface. But that was proposed in the literature, and yeah. And if you put a CO in first and put NO later, then you can form that. And you put it in the other side, usually you don't form it. So it has been done extensively in literature.
Migrates in the gas phase.
I don't care how it migrates, I want to know how it forms.
And that species was proposed as a precursor for the N2 formation in the Z-like catalyst.
Yes, Bruce.
Stephen, could you just summarize what role do the CO bonded to the rhodium cations play in any of these reactions? And what role does CO bonded to zero-valent rhodium play? Summarize what the roles of these species are.
In what reactions?
Well, try CO hydrogen or CO hydrogen with those.
Okay, we have studied the reaction of these with hydrogen, but we couldn't distinguish which one is more active. But in the CO insertions reactions, right, we found this is the most active one. Then this is secondary, this is second, this is third. In this sequence, we have studied rhodium chloride, which is a primarily, if we put CO of rhodium chloride, you produce primarily the gem dicarbonate. And we also studied the oxidized rhodiums, which give these two species. We also studied the rhodium prepared from rhodium carbonaceous RH6CO16, and after you expose to air, you produce this species. So we compare this reactivity of this species at different temperature and different pressure. We found this is most active, and this is the second one, this is third. But under reaction condition, hydroformylation condition, we have, it's about 100 degrees C. Most of these species are reduced because of the hydrogen. So this is the most active one at the room temperature. But under the high temperature, at temperature of 100 degrees C, in the presence of hydrogen, this guy usually start to get reduced, and only this guy left. And in the CO hydrogen reaction, the methane bank is very weak, and we really rely on mass spec, and we always get ambiguous result. We don't know which species is more active. we couldn't get a conclusive result. And this is a speculated species, and we found this is not active for CO insertion at all. Ichikawa has suggested that. And Sakura has suggested a long time ago, but I talked to Sakura last year and he changed his mind. He found this is look like a speculated species.
Do you have data on the rate of interchange of those various species? That is, for example, you've got a couple of linear and your gem dichar. How fast do those things interchange with each other?
These are very rapid and much more rapid than our FDIR or mass spec. And because of flow, it relies on the flowing, the reactant flow through the system here. So those are much rapid than our reactant flow and our scanning speed of infrared spectroscopy. So we don't have the rate data for that at all.
Okay, well now if, this just shows you because I can't think that fast enough, but I worry a little if species interchange with each other very rapidly, then how does one say which one is then doing the reaction with, say, your ethylene to do your CO insertion reaction?
Or
You can tell that something disappears.
yeah, we worry about that too. For example, in this case here, the bridge CO may exchange with linear CO and react.
Mm-hmm.
So we try to confirm that by blocking the bridge CO side, by silver or sulfur. And we found when bridge CO got killed, the catalyst can only absorb the linear CO, and those catalysts remain very active for CO insertion. In fact, it's more active and more selective. And we have published that result in Journal of Catalysis in 1992. Yeah. So we worry about that too. Yeah.
Yeah, okay, yeah, that's very nice. Any other questions at the moment? So I think that's a beautiful piece of work, actually showing. We are getting down to, we've had several papers now looking at intermediates and showing that with infrared spectra we really can see some intermediates, which is after Bob Eischen started this business a good many years ago, we didn't find very many active species, as I believe John asked the question about a little earlier, but now we certainly are beginning to find active species on the surface with the infrared. Well, thank you very much. Our next paper